We're about to start an exploration, and we're going to take some ideas and they will lead up to a new formula. So that process is called deriving, different from differentiating. Those are different words. Deriving just means taking old principles and getting something new out of it. I want you to try to enjoy the ride for the next couple slides. Please don't look at the next couple steps that we're looking at as ones that you need to recreate. Instead, so I want you not to stress out about it. I want you to just kind of follow each step and go, okay, that's what's going on here. That's what's going on here. Please do not let this thought enter your head of, oh, wait, I have to know how to do this and recreate each step. No, please don't think that. There are a lot of steps in what we're about to see. I just want you to see the process because you can see where everything is going to come from. That said, you will not need to recreate this process here. Okay, so this is leading up to a nice little formula. Okay, so we got W equals capital F of x comma y. So there's some function called capital F, and then y happens to be written as a formula that only depends on t, and we'll call that h of t. X depends on only t, and it's a function called g of t. And the question is, what is dw dt? So let's just suppose for right now that we don't know h of t or g of t yet. So, you know, in practice we may, but if we pretend we don't right now, this helps in creating a more generic formula that we can use in all kinds of situations. So let's take a look at what we have just in terms of the ideas we've already seen. The dependence diagram is that the output variable w depends on x and y. So we have w down to x, w down to y, and then x and y each depend on t. So we have here an arrow from x down to t and from y down to t. And then on the arrows themselves, I wrote the specific partial derivatives that we would be talking about. Yeah, so you see a dw dx on the arrow from w to x, which we could also call capital F sub x. Okay, you'll notice that down here, like the arrow from x down to t, says dx dt without the curly d's, with the regular d, because x only depends on one variable t. And so this is a standard Calc 1 style derivative. So if we write down what the chain rule should tell us, it's that dw dt should be dw dx times dx dt plus dw dy times dy dt. If we just replace a little bit of notation, dw dx, its other notation was capital F sub x, and then dx dt, well, up here x is g of t, so the derivative of x with respect to t is, using standard Calc 1 notation, g prime of t. Same story, same general story for the next term. Now let's just say that we learn now, right? We suppose in the blue box that we didn't know what h of t or g of t were. We just pretended we didn't know their formulas. But now let's say we were given this additional information that g of t equals t. Okay, so the formula for x is just x is literally equal to t. Nothing, it just, we up until now had assumed it could have been more complicated, and so we were talking in a more general setting. Now we know g of t is t, so g prime of t is equal to 1. And let's now make a replacement based on that. So f sub x times 1, just left that out. And now what I'd like to do is take dw dt equals this thingy here, f sub x, plus f sub y times dy dt to the beginning of the next slide. So in addition to that equation that we just mentioned, let's also now say we're going to add one more piece of information in, that capital F of x comma y. It looked like some complicated function, but let's just say that it happened to always equal 0. That can occur, and we'll talk about a setting in which that happens in a moment. Then what? Well, so remember w was our output variable for saying what capital F was. So if w is really 0, then dw dt equals 0. So we'll replace the left side here with a 0. We have 0 is equal to f sub x plus f sub y times dy dt. Now let's solve for dy dt. If we solve for dy dt here, subtracting f sub x on both sides and then divide both sides by f sub y, you have dy over dt equals negative f sub x over f sub y. So recall also that we had started with x is some formula of t, but we left it generic, calling it g of t at first, and then we later said, oh, somebody clued us in that g of t equals t. Oh, so since x equals t, So since x equals t, what we could actually do is literally take the equation above, dy over dt, and now just call it dy over dx instead. So implicit differentiation is this new formula for it. It's a new technique, okay? So if you have capital F of x comma y is a function of two input variables and its output is always 0, then the derivative of y with respect to x is equal to negative f sub x over f sub y. I know it's a little strange that the partial with respect to x is above the one with respect to y. It looks like it's flipped from what it should be or something like that. But that's why we went through the steps. So you can review the steps if you'd like. Every step really works. I hope you're convinced one step to the next it works. And you don't need to memorize all those steps or anything like that. The point was to lead up to this. The point of showing you all those steps was to try to now say, when somebody wants to ask, well, why is it negative f sub x over f sub y instead of the reciprocal? Or why is there a minus sign in front? And the answer to that all is, it is what it is because the previous 2 slides worth of work is the proof that it is what we have shown it is. At the same time that this proof has been stuck in here, you are not going to ever be expected to recall the proof. You don't have to recreate it. But I do want you to see how this formula gets used. So let's look at an example of this. We will use this on occasion in the final chapter of this semester. So here it is, just first of all, the formula that if you have capital F of x comma y, it's a function of two input variables, and it happens to equal 0. And you might say, when does that ever happen? We'll see in a second. Then our new formula is that the derivative of y with respect to x is negative capital F sub x over capital F sub y. So let's say you have this scenario. Now this looks a little strange, but we've got x cubed plus y squared plus y e to the x equals x sine of y. And let's find dy over dx. Oddly enough, the implicit differentiation formula at the top applies. And you might say, how could this possibly apply? We need a function whose output is always 0. And what we do is we need a capital F of x comma y equaling 0. Where is there even a 0 written above? Well, let's create that. Subtract on both sides. And if this equation here is true, then you have x cubed plus y squared plus y e to the x, that was the left side, minus x times sine of y equals 0, right? So that's just an equation that's true. And then we'll just take the left side, which is, we know, equal to 0, because that's what we were supposed this equation up here. We're going to call that capital F of x comma y. So we have created a function. It's a little creative, I get, but like there's this function that we created so that we can apply this implicit differentiation formula. Now to find dy over dx, let's just compute the pieces. So looking at capital F as underlined here, the partial derivative with respect to x is 3x squared plus y e to the x minus sine of y. The partial derivative of what's underlined with respect to y is 2y plus e to the x minus x cosine of y. And then literally just following this formula, we have dy over dx equals negative sign and then a fraction where the numerator happens to be the partial with respect to x first and the denominator is the partial with respect to y next. I know this all looks a little funky. It seems a little odd, but we have to trust what's in the box up there, and to trust what's in this box up here more, it requires really just digging into the proof that you saw the prior 2 slides. If you'd like to, I would suggest that you try finding dy over dx in the situation that x cubed plus y cubed equals 6xy. You don't have to do this, but I would suggest it. Once you've just worked it out on your own, this is worked out in the textbook. So please take a look at that.